So, there's only one thing that we've done so far that has been specifically related to an SOL that we're supposed to cover. That was the properties we did on day one. The solving equations, the expressions, solving equations, and inequalities that we just covered, those actually are not in our Algebra 2 SOLs. They're just review. This one is in our Algebra 2 SOLs. Okay, this is the first one, and we get a lot. Yes? No. Right? Do not ask me to go to the restroom. When we're all done with our lesson and you're taking your quiz, if you want to spend some of your quiz time to go to the restroom, that's fine. As long as you're back and you finish by the end of the block. Okay? This came from a lunch block. Yes? Huh? Oh, yes. It will be on the test. Okay, so that's our one SOL, one statement here. So most of you know what absolute value means already, right? Absolute value is the positive distance from 0 on a number line, right? Meaning it doesn't matter if I'm at -3 or +3. It's still 3 away from 0. So the absolute value of a positive number is positive. The absolute value of a negative number is positive. Always positive. Right? It would be not, if you had something like true or false, absolute value always switches the sign. And you would say false. If it's true, it doesn't. If it's positive, it does not switch the sign, right? Only when it's negative, it switches the sign. Yes. Those are called absolute value symbols. Okay. Learn the vocabulary. Okay. We good? Ashley. Okay, hurry up. Remember, you can download all this stuff on our website. And if you're taking the time to copy all these notes and you start going over your homework, don't raise your hand on the first question and ask me to teach it to you again. Look at your notes, right? That's what happens every time. You get the first question. I don't get it. That's what I call a helpless hand raiser, okay? Look at your notes. You just copied them. We're going to spend all this time letting you catch up and do all your notes, and by all means, look at them. Right? Are we done? We're done? Okay. Okay. So we have to do three things. We have to do absolute value equations, absolute value less thans, and absolute value greater thans. And they're all just a little bit different. A lot of similarities, a little bit different. If you have something as simple as the absolute value of x equals 5, then what it's saying is, if I plug in a positive 5 here, what will be the effect of taking the absolute value? If I put in a positive 5, what happens to the absolute value of 5? It's still the same. So 5 equals 5, that's true, right? So that's true. What if I put in a negative 5? Then when you take the absolute value, it flips the sign, and it's true. So whatever's inside the parentheses, it either equals this, or it equals the opposite of that, right? That's the way it works. It's either got to be 5 or negative 5. Okay, well, most of the time, yes. Here, these are operators, right? It says whatever's inside, if it's positive, leave it positive. If it's negative, flip the sign and make it positive. Okay, most of the time, what's inside is not going to be as simple as like an x. It's going to be some kind of algebraic expression, like what we studied on the first day, right? There'll be some absolute value of an expression equals a number. I'll just call it c. Right? So what we will do is we will set that expression equal to the right-hand side, and we'll set it equal to the opposite of the right-hand side. So we'll have two equations. Right? If I was doing this, then I would have said x equals 5, x equals negative 5. Two equations. So you solve them both, and you get two answers. You always expect two answers. Okay, and it's important, this thing here, when you go from this step to this step, these equations, these two equations, no longer have absolute values in them. Okay, we're trying to do something to lose the absolute value symbols. This will make more sense on the next example. Yes? Not going now. Okay? No. Okay, here would be an example, right? We have an expression that's inside the absolute value symbols, and it's equal to 5. So we're going to set the 2x minus 1. If it equals 5, then when we take the absolute value, it still equals 5. Right? So that's one equation. 2x minus 1 equals 5. Okay, but what if that 2x minus 1 equals negative 5? Then when I take the absolute value, it equals positive 5. So make another equation. 2x minus 1 equals negative 5. Right, that's always step. And notice, now there's no absolute values in those two equations. Right? Because here's the thing. You can't do math. You can't do the algebra if you got the absolute value symbols there. Right? You can't do algebra with things that are inside and things that are outside. Like I couldn't come here and say plus 1. That's not allowed. But with these two equations, I can, because there's no more absolute value. So now we're going to solve these two equations. They're pretty basic, right? Plus 1, 2x equals 6, divide by 2, x equals 3. Right? Add 1. 2x equals negative 4. Divide 2. X equals negative 2. So we did something to lose the absolute values. That meant breaking it down into two different equations. We solved both equations. We got two answers. That's what you expect from absolute value equations. Now, the next. Here's the steps. For an equation, these are the steps. Okay? It's not always the case, sometimes the case, not always the case, that when you start the problem, the absolute value is the only thing on that side of the equal sign. But it's very common that it would look something like this. So you would have a first step, which is isolate the absolute value, meaning get rid of the things that are with it. Right? What's with the absolute value on the left-hand side that you've got to deal with? Say again? The 2 and the 3. So you've got to isolate the absolute value, you've got to get rid of the 2 and get rid of the 3. How are you going to do that? No, you would never distribute. You cannot do this operations with numbers inside and outside. Can't work. Yeah, I mean, just think of it, if this was just a regular old algebra equation that said 2x plus 3 equals 7, then in order to isolate, you would subtract 3, divide by 2. That's exactly what you do. Okay, so subtract 3, 2 times absolute value of x plus 9 equals 4. And then divide by 2. So absolute value of x plus 9 equals 2. So that's the first step. Isolate the absolute value. Okay. The second step, now we're going to undo it. We're going to do something to get rid of the absolute value, which means write two equations. What are the two equations? Right. X plus 9 either equals 2 or it equals negative 2. Because when you put the absolute value around it, it'll both equal 2. So write it down like this. X plus, oops, that was wrong. X plus 9 equals 2. X plus 9 equals negative 2. Two equations, solve them both. X equals negative 7. X equals negative 11. Two answers. And if you need be, you could plug them back in, check. See whether you got the right answer. Just like any time you solve an equation, you can always check that way. Yes? Yes. They're both right. They're both right. I mean, do they both satisfy the equation? Put in negative 7 here. Negative 7 plus 9, 2. 2 times 2 plus 3 is 7. Put in negative 11. Negative 11 plus 9 is negative 2. Absolute value is 2. 2 times 2 plus 3 is 7. So they both solve it. Yeah. That's what you expect. Absolute value, two answers. So try that one. Try to do the same thing. Isolate, undo, solve, check. Let's see. Correct. Do you want to do it up there? Okay. No, because I wouldn't hear you anyway, because I got the earpiece. Parker's going to put his solution up there. Good job. How are we doing? Yes, yes. Listen. Incorrect. Add 1, you get 9. Good job. How'd we do? Negative. How we doing? Super. No, you can do it. That's right. What? You add 1 to both sides. That becomes a 9. We'll deal with that later. Just like we did, where's the example I just did before that? Because you're sleeping over here. I was sleeping over here? I was like this. Okay, well, you didn't take a note on it. So you have nothing in front of you like to base your work. What's that? I'll send you a few minutes early. How'd we do? 1, good job. Good job. So then move up. Just empty seats. Good job. If you don't like teach your equations, the negative, can you still figure out which is one? You need two answers. You got one answer. That's going to get partial credit at most. Okay? So we see what he did there? He added 1 to both sides, get the 9. Divide by 3. Absolute value of x plus 2 equals 3. Right? Undo the absolute value. X plus 2 equals 3. X plus 2 equals negative 3. No more absolute value symbols. Solve them both, 1 and negative 5. Good job. Thank you. What'd you do with my pen? An apple? Oh my gosh. What am I going to do with an apple? Okay. Okay, now this one, how does this one look different than the one we already did? Curtis? Yeah, it has a variable inside the absolute value, and it has a variable outside. Yes? No, I'm going to show it. There's a new thing to show on this. But it still works the same way. Remember, our process right now is isolate the absolute value. It's already isolated, so that won't be a part of this. Second step will be set what's inside equal to the right-hand side, and then set it equal to the opposite of the right-hand side. Just like we do, we don't set it equal to 5, set it equal to negative 5. Same thing. We're going to break, here's our two equations. 5x minus 2 equals 7x plus 14. And the other equation will be 5x minus 2 equals negative 7x plus 14. Right? So we're setting it equal to that, just like it is, and then the same thing with a negative in front. I mean, if that was a number, it'd be like 5 and negative 5. Yes? Why do we what? Subtract? I'm not sure what you mean. Do you mean distribute? Yeah? We will. And you know, you might have, most of you guys in here are smart enough to say, just in the first step, you might have just done this anyways, which is negative 7x minus 14. Okay? Yes, you could do that. Just make sure that you don't just like put a negative here and forget that that also changes the sign of that. Now, let's solve them both. These are both still linear equations, x to the first. We can isolate the variable. Subtract 5x. Negative 2 equals 2x plus 14. Subtract 14. Negative 16 equals 2x. Divide by 2. X equals negative 8. Okay? Solve the other one. Which is the smaller of the variable terms? The negative 7, right? Negative 7 is less than positive 5. On the number line, it's to the left. So we have to add 7x to both sides. 12x minus 2 equals negative 14. Add 2. 12x equals negative 12. Divide by 12. X equals negative 1. Okay. So we got our two answers, which is what we expected. Now we have to take that, we have to check. Okay. And here's the thing. When you've got variables inside and outside, it's very probable that one of these answers will not check. Okay. That's why it's especially important to check your answer in this kind of a problem. In the other kind of problems, I mean, it's fine. Check your answer. It's always good practice, right? But on this kind, notice what happens. Let me check this negative 8. If x equals negative 8, what does the right-hand side equal? If I plug in negative 8 here, what does it equal? 7x plus 14. Plug in negative 8. Negative 42, right? 7 times negative 8 plus 14 is negative 56 plus 14, which is negative 42. Okay, so we're saying here that this absolute value equals a negative number. Is that possible? No, absolute value is always positive. There's no way that the right-hand side could be negative 42. That means this is not an answer. So when you solve and you get this answer, you did everything right, but it doesn't check, that's called extraneous. It's an extraneous solution, right? So we have to write that down. extraneous. Which means it's not a solution. Okay, it's not a solution. But you don't know until you've solved it and then plugged it back in. No, I've never seen one where they're both wrong. Doesn't mean it's not out there. They can't construct one like that. I've seen them where they're both right. Okay, so extraneous. There's actually, we're going to use that word over again. When we do radical equations, there's also extraneous solutions. When we do rational equations, there's also extraneous solutions. So it's not the only time we're going to see this word, extraneous. So this one is actually not, now we could check the negative 1. Put in negative 1. 5 times negative 1 minus 2 equals 7 times negative 1 plus 14. Okay. What is 7 times negative 1 plus 14? It's positive 7, right? And what is 5 times negative 1 minus 2 is negative 7. The absolute value is positive 7, right? So that one checks. Right? That one doesn't. Okay. So that's what you need to, that's everything you need to know about absolute value equations. Yes? Okay. Okay, now we got to do two kinds of inequalities, right? Less thans and greater thans. And by less thans, we mean less thans and less than or equal to. So it's the same thing whether it's or equal to or not. Okay. So let's try to if you look at this, again, most basic example of an absolute value less than, the absolute value of x is less than 5. Would 5 be a part of the solution? Is 5 less than 5? No. So that tells me that we've got to have open circle here. Would negative 5 be part of the solution? The absolute value of negative 5 is 5. 5 less than 5? No, we already said no. So that's an open circle. Okay. Would 4 be part of the solution? Okay. The absolute value of 4 is less than 5, so that's good. In fact, all the numbers less than 5 until you get to 0 are good, right? Because they're less than 5 no matter what. And then we get to 0. What about the numbers that are less than 0 but not less than negative 5? For example, what about negative 1? Would that solve this? The absolute value of negative 1 is 1, right? That would put you over here, and that's less than 5. So, in fact, all the values between 0 and negative 5, when you take the absolute values, their values are in between 0 and 5. So they all solve it. How about negative 6? What do I go on the other side of negative 5? Would the absolute value of negative 6 be less than 5? No. So that's the solution right there. All the values in between 5 and negative 5. And usually the way we write this is with a three-part inequality. Negative 5 is less than x is less than 5. Right? So it's telling you on the left, it's bounded by 5. On the right, it's bounded by, negative 5. On the right, it's bounded by 5. And the shading, the x, is everywhere in between. Okay. Right. Well, again, most of these are not going to just be x. It'll be some expression in absolute value is less than a number. But we still expect the same kind of graph, right? It'll have a bound on the left and a bound on the right and the shading in the middle. And the way we're going to solve it is by writing a three-part inequality. And we did see a little of three-part inequalities in the last lesson. In the presentation of the lesson, I don't think there was homework that did it. But basically, a three-part inequality like this one right here is a compound and. Right? It's telling you that both x is greater than negative 5 and x is less than 5. Right? It's an implied compound and. You don't see the word, but it's there. Okay, so we have very similar steps, just a little bit different. First, we're going to isolate. Then we're going to undo the absolute value by writing a 3-part inequality. And we'll solve it. Because our expression now is in the middle, you have to solve for x in the middle. And then we graph it. Okay, so the first step is isolated, so I don't have to do that. Now we need to write a 3-part inequality. And remember, the 3-part inequality has no more absolute value symbols. And the absolute value symbol, and with the expression, is in the middle. So what goes on the left and what goes on the right? 5 is on the right, -5 is on the left. 3 parts. Okay, now we're going to solve for x in the middle. I mean, look at the middle. This 2x minus 1. What do you got to take away so that that x is isolated in the middle? You got to get rid of the 2. You got to get rid of the -1. Which one are you going to do first? +1. Okay, but now because there's 3 parts, it's not an equation with 2 sides. It's got 3 parts. If I add 1 here, I have to add 1 here and 1 here. This is -4, less than 2x, less than 6. Okay, that's still not isolated yet. What do I need to do to isolate x? Divide by 2. Here, here, and here. Okay, now we have -2 is less than x is less than 3. So x is in between -2 on the left and 3 on the right. That is the answer. So here's -2. Here's +3. Should I make open or closed circles? Right? They're both open, right? Less than, less than. So open circle, open circle. Where does the shading go? In the middle, right? The x is in between -2 and 3. In between -2 and 3. Oops. That's the graph. Now, how many of you remember doing this sometime in the past? And how many of you did not use 3-part inequalities when you did it? And I would just say for most of you, this is the right way to do it. People that don't teach that probably are not very good at math, especially if they're like 6th or 7th grade teachers. They may not actually had any intention of teaching algebra. That's why they taught the lower grades. If they wanted to teach more complex math, they would have gone to high school. But we keep pushing this stuff to lower grades, and you get people that it's really not their strength, and they do their best. They may be in some ways good teachers, but this is the way you should deal with it. If, for example, you decide to do it as 2 inequalities, which is the other way they could have told you, then you would have to do it like this. You would have to say x, oops, I don't like that. You would have to say x is greater than -2 and, right, x is less than 3. It would not be right if you didn't put that and in there. Yeah. Yeah. Both when you get to absolute value inequalities, it almost always says graph. Graph, graph, graph. Yes. The equations, not so much. Although the SOLs, it was always unclear to us whether they meant for us to be graphing absolute value equations, because what are you going to see on a number line if you graph the solutions to an equation? 2 dots. You know, like here's a dot, here's a dot. I mean, with inequalities, because it's got shading involved, you really do have to graph it to see what we mean. For an equation, I don't think it's the same thing. Okay, so try that. make a three-part inequality, solve for x in the middle. What's that? And graph. Yep. Solve and graph. No. What did we do here? Where's the one I just showed? Okay, well, that helped you right now. That's not what we did. We don't just erase it. Okay, we put the absolute value in there, and on another line, make a three-part inequality. What goes in the middle? What goes on either side? What? It's okay if you get a decimal or a fraction. That's okay. Why would it not be okay? Let's switch that. Where's your three-part inequality? I mean, how hard is this? There's the expression. What goes on the right? What goes on the left? Did you write down any of that? Okay. That's good. Negative 4/3. Just write that. Negative 4/3. Good job. I'm seeing a couple good answers. Remember, this is an inequality, not an equation. It's a three-part inequality, not two equations. And that's good. Okay. Do you want to do it? Okay. Doing all right. And incorrect. Why didn't you do a three-part inequality? I'm just saying, even if you did it with two, that's wrong. You didn't set it up right. Yeah. Perfect. Good job. It's good. And where's, try that again. What's 12 over 3? 4. Why did you mark 3? And then you got shade.
Yeah, I don't know why too.
In between. X is in between negative 3/4 on the left and 4 on the right. So in the middle. Now you have to decide whether it's open circle here or closed circle. Which one is it?
Open.
Yeah, because it's not or equal to, it's open.
Okay.
Yeah. Yeah, so partial credit. Which one is that? The first one? Okay. Is it just this? Okay. Okay, graph. Graph. Good job. Okay. So that was good. Everything just the way I would prefer you did it. Now again, I know that you were taught, you might have been taught differently, and I would just say you need to learn how to do three-part inequalities. If you don't, then you got to set it up like this. You got to have one equation, which is 3x minus 4 is less than 8. Oops, that was wrong. Is less than 8. And then you got to have a 3x minus 4 is greater than negative 8. And then you solve it twice and you make sure you got a hand in the middle. So there's something to remember when you do that. And what I saw going around, there's at least one that tried to do it that way, but then didn't have that one set up right, didn't have a word and. It doesn't matter. Okay, now we do the last one is a greater than, right? And by greater than, we mean it could be greater than or it could be greater than or equal to. Okay. So again, let's look at the number line and try to imagine where on the number line is this going to be true. First, will 5 solve this? Would the absolute value of 5 be greater than or equal to 5? Yes, because of the or equal to, right? So that definitely we want the 5 right there. How about negative 5? Sure, when you take the absolute value of negative 5, you get 5. We already said 5 solves it. What if we put in a 6? Is the absolute value of 6 greater than 5? Sure. So the shading is going to go that way, right? What about the numbers in between 5 and negative 5? Right? I mean, if I take the absolute value of 4, it's clearly not greater than 5. Or negative 4, the absolute value is still positive 4, not bigger than 5. So the shading is going where? It's going to go here, right? It's going to go to the left of negative 5. Okay. So let's write an inequality that describes this right here. This would be x is less than or equal to, x is less than or equal to negative 5. Okay, write an inequality that describes that. Positive 5, right? X is greater than or equal to 5. Right? And then this is a compound statement. We got 2 different inequalities, and it's tied together with an or. Right? So the solution is both of those with the word or in the middle. It's either here or it's there. All these points, yeah. Well, if it's an and, if this was an and, what would be the solution if this was an and? Are there any points on the number line that are in both, that overlap? No. This would be no solution if it had an and. Right? This one, if I would have solved it with 2 different inequalities, I would have had like this, and the solution would have been where they overlapped. Okay. Okay, so generally, we will not have x inside just x by itself. It'll be some kind of a variable expression that includes x. In absolute value is greater than or equal to a number. And the way we will undo it is we will write 2 inequalities. We'll make that expression greater than or equal to the number, or we'll make it less than or equal to the opposite, right? Just like this, x is greater than or equal to 5, but x is less than or equal to negative 5. Right? You got to flip the inequality. You got to make that sign negative. So here's our steps. Again, very similar, but a little different. Still we isolate, and then we undo. For a greater than, we undo by writing 2 inequalities, and they are a compound or, right? They're tied together with or. We solve them both. We keep the word or, and we graph. So let's see. First step, isolate. What do I need to do to isolate? Okay, add 5, right? So add 5 here and here. Absolute value of 5x plus 10 is greater than or equal to 15. Okay, we isolated. Okay, what are the 2 inequalities? Let somebody else catch up. John. I can't hear you. I can't hear you. I didn't hear you. No. No. Go ahead. No. Yeah. Well, it's not a three-parter anymore. It's two completely separate inequalities now, right? Yeah. Yeah. What? Okay. It's basically this thing without the absolute value symbols, right? So that's one. Okay. And then what's the other one? Right? So the other one is switch the sign, switch the inequality, and make it a negative. Yeah.
So can you never put them together?
No, not for a greater than.
Okay.
Yeah, these two are never, going to be where you could like put them together in one three-parter. It would not make sense, right?
Only works when they overlap?
Yes, only for a less than. Okay, now solve both of these. Yes. Because, again, go back to what we just did here, right? This was x is greater than 5, greater than or equal to 5, or it's less than or equal to negative 5. It's to the left. That's why we flip the sign, right? It's because it's less. Okay, solve. Minus 10, 5x is less than or equal to negative 25. X is less than or equal to negative 5. Okay, and subtract 10. 5x is greater than or equal to 5. X is greater than or equal to 1. Right? It's both of those tied together with the word or. It's a compound inequality. Without the word or, it's not fully right. It's partially right, but it's not fully right. Okay, so then graph. So the negative 5 is on the left. Positive 1 is on the right. Do we want open or closed circle? It's or equal to, so it's closed and closed. Okay, if it's less than or equal to negative 5, which way am I shading? Yeah, I'm shading this way. And if it's greater than or equal to 1, which way am I shading? To the right. Okay. And that's what an absolute value graph looks like. An absolute value greater than, right? It's the ends are covered, the middle is not. For the less than, the ends are not covered, the middle is. They have completely different looks.
Good afternoon, K-Town Warriors. I apologize for the interruption. This is Mr. Mordecai, principal. Teachers, once again, I apologize for the interruption, but I just sent out an email that I asked that you read. It is important that you look at this information so you are aware of communication. If you could please look at your email at this time, that would be greatly appreciated. Thank you for your support, and if you have any questions, please contact the main office and let us know. Thank you.
Okay. Okay. There's nothing we just have one slide left to go here. Maybe two. Okay, quiet please. Quiet please. Oh, that's right. Okay? So tell me, these are situations you see sometimes as a problem. Would it be possible, would you say that it's always true, never true, or sometimes true if you had an absolute value of an expression equals a negative number? That can never be true, right? Because what do we know about absolute values? They're always positive. So there's no way that this could be true. That's a never. Okay. How about this one? What about if you had an absolute value of an expression as less than a negative number? If the absolute value is positive, could a positive be less than a negative? That's a never true. And what about if you had an absolute value is greater than a negative number? Always true, right? Because positives are always bigger than negatives. Okay, so that's it, always. And when you see a problem like that, you may be just going along doing your homework, you get a problem that actually is like that, and you start applying our steps, and you wonder why it doesn't come out right at the end. But if you recognize it at the beginning, you just say it's not true, or it's always true, and you don't have to do anything. Yeah. Well, sometimes they're like that, right? This one is true when x is greater than or equal to 1. It's true when x is less than or equal to -5, but it's not true in here. Okay, last thing. This is taken from a book in your picture in your book, which is right here. It says in car racing, a car must meet specific dimensions to enter a race. The officials use a template to ensure that these specifications are met. What absolute value inequality describes heights of the model of a race car shown, within the indicated tolerance? Okay, so they're saying they want the height of the car to be 52. It would be okay if it is as tall as 53 or is as short as 51, but it's got to be somewhere in there. Okay, and so this is the range, right? It can be anywhere from here. I'll put a closed circle, or it could be in between. Any of those heights of the car are okay. So first of all, we're doing a section which is about absolute value, right? And we have for inequalities absolute value less thans and greater thans. Which one does that look like? Remember what they look like. That's what a greater than looks like. That's what a less than looks like. Which one does it look like? It's a less than. So we're looking for an absolute value less than. So we know we're shooting for 52, but we need to make sure that it's no more than one difference from that. And you might guess how we do that. If we're going to call the height of the car the h, the way that you would write it is like this. You would say the absolute value of h minus 52 is less than or equal to 1. Right? You see how if I'm anywhere between 52 and 53, what do I get when I subtract 52? I get something less than 1. Right? If it's 53 and I subtract 52, it's 1. If it's between 51 and 52, then when I subtract, I'm going to get a negative number, but it's between -1 and 0. I take the absolute value, it's less than 1. So that's a typical way to try to represent some kind of a process where you're shooting for a middle number, but you'll accept a certain range around that. Right? And the range that you're accepting, that's called the tolerance. I think there was an SAT question that we used to go through. It was something like this. There's an assembly line, bottling soda, and they're trying to put 12 ounces in the can. And then at the end, they do some random sample. They try to pick it out and see, well, how much did we actually get? And they would accept anywhere from 11 7/8 to 12 1/8. If it was anything more or less than that, they throw it out. So there's a tolerance of 1/8 of an ounce. And those are very real things that people have to deal with in jobs, you know. I mean, because nothing's ever perfect. I think there's one homework that's like that. Okay, one homework. Okay. So that's what we did. That's the homework. Write it down. And then we're going to take a quiz. Yeah.